So the way I did it in this example is I basically linearized the whole array. So I used that I know that this is a contiguous array. NumPy arrays are contiguous arrays. This is a good thing as well. And so I can know that I have rows and then the next row and the next row. And so so once I've unraveled those as if they were linear, shifting to the left is just going by one way or another. Shifting a row, I just add number of points, and that actually shifts me number of points, which is the next row. Again, a piece of paper or a whiteboard, very useful in these cases. Once I've created the left, right, up, down, and central versions of these densities, I can put them in my evaluate. So, and I'm using a slightly different way in which I put the output into a known quantity, which can emit one copy. So that's what I did. Not the most beautiful thing you do. You'll do this if you need that last bit of performance, but it does help. Questions? Okay, so that is OpenMP for Python, although it really isn't. But that's oh yeah. Okay, so that's okay. What else can we do? What else are people throwing at us saying, hey, you should use X? Numba. I mentioned it briefly already, but it is the Numba package is a package that can take a Python function and compile it. That's the road we want to go. And it's decorator based, so it actually will take a function, you put a decorator, it's not going to be at profile, it's going to be at JIT for just in time. And it will take that function and basically compile it. So that's a little bit like compiling our expression, except it's not a string that we have to give. It's a function, and it's more versatile. So it can do slices. It can basically do any Python thing. Now we want to be careful, but it can do anything that Python can do within reason on a CPU. On a GPU, it's different. So it can do GPUs. I mentioned that already. But what you can do with GPUs and how you program that is quite different. It's not just adding a decorator to your function. So it's not like OpenMP offloading at all. It's more like writing CUDA. Anyway, we were not going to look at that, so maybe not. But you can use multi-dimensional arrays, slices. It can vectorize on multi-core. It can use GPUs, but that's a bit complicated. How does that work? So the first thing to realize is that we can't latch on to a for loop. We can't latch on to a single expression. So we have to put our expensive part of the code into a function. And again, how do we know what the expensive part is? Well, we profiled it, and we know. So this was the expensive part of our code, Laplacian, dense next. And so we're going to put that in. So that was the old code. It took about 2.2 seconds. We're putting this in a function. We just give it a name. Obviously, it'll need some arguments to be passed in, so it's a bit of an ugly function, but there it is. And in front of the function, we're putting at JIT. JIT comes from Numba. So we've installed Numba, we'll import JIT, and that will take this function and basically have it compiled the first time it is called. So if it's not called, it's not compiled. That's nice. If it's called, it's compiled. If it's called again, that compiled version is used. And so whenever we had the for loop, we just called the time step function. And it's slower. So the non-Numba version, the NumPy version is 2 seconds. The Numba version here is 6. And again, there's it works. This is the right thing. But can we do it better? We can do better. But, sorry. I think I changed the font size and didn't look at every slide. But why is the performance so, let's call it limited? So it's because Numba does compile the code, but what's the code asking us to do is to call NumPy. So it calls NumPy. And so we have the NumPy cost, which wasn't too bad, and then we have the overhead of compiling this function. and of calling that compiled function. So there's something funny here. We've reached a good level of performance with NumPy by vectorizing, but now we're kind of stuck and we can't get beyond NumPy, so we have to get out of NumPy. Whereas we got so much by getting into NumPy. So let's try this then. Let's take the original code. The original code was a bunch of for loops. It's a just-in-time compiler, so when it's called, it can see what the types are of the things that are in here. And so it should be able to do what I mentioned before and go, okay, these are arrays of floats, and so these for loops are just for loops, and we'll compile them as such. And when you call them with different types, we can compile them for those types. And that works. The performance is still not fantastic, but at least we're back at something reasonable for the code. So this is funny. This was the slow code. If we didn't have the @JIT there, we would get back our 200 seconds. So while it's true that it's better to use NumPy and vectorized operations, sometimes it's kind of nice to say, okay, let's take the code, put it in a function, and pass it to NumPy, and see what it does, because that might also be enough. Maybe NumPy arrays aren't the way to go. You'd still want them to be arrays, but you might not have to vectorize your code. Funny, right? Questions? Yeah. Mm-hmm. Good question. So the question is it possible to combine the parallelism of NumExpr with the compiled nature of Numba? And people have asked Numba that, and Numba said, yeah, sure. Let's do it in parallel. But it doesn't work exactly the same way, and that's actually a good thing. This, again, gets very close to how you would OpenMP a loop. So you would think, well, just give it parallel equals true. So there's an extra argument here, and we're done. But we're not, because there are no proper automatic parallelization compilers, and Numba is definitely not better than your, not magical in that sense. So you can ask a compiler to automatically parallelize your code, but if you didn't say what parts can be parallel, nothing good will come of that. That's why in OpenMP you have to say what loops can be parallelized. Same here. But how do we do it here? It's not a pragma. It's not a directive. You have to change your range to a p range. So it's kind of subtle, especially if you hadn't noticed the extra p here, and it's not a typo. I have to have both parallel equals true. That will start my threads. It's like OMP parallel. And this is like your OMP4 saying the range that we're going here, everything that's in that for loop can be done in parallel. So this is your work sharing construct. It's very hidden here, but it does exactly what you, if you've done the OpenMP for loop stuff, it does exactly that. It takes your for loop, or your range in this case, it splits it up over the different threads that you might have. By default, I think it uses all the threads it can get, and parallelizes that. So use p range instead of range, and that should be happening. Does it work? It works. Mileage really varies with these kinds of applications, and it's true that the amount of work in the inner loop isn't really that much work. Like every row doesn't do that much, so whatever overhead there is, we're going to feel it. So this is just sort of on the edge. Again, if you wanted to see more, you could make your grid larger. The reason I didn't do that initially is that 200 seconds for my initial Python was more than enough to wait for. I've given this workshop before, and we had to wait 2 hours for the first result to come in, and I went away from that because we would not be doing anything yet. But if you had a bigger grid, you'd see more speed up. And this is generally true, obviously. So if you have anything that is more complicated than just some additions, the for loops are more complicated. I think if there's if statements and stuff like that, Numba can really make a difference. And we don't have to go the whole route of changing our code into Python for specific types and all of that. So it's a little bit more flexible, but it does cost some time to compile. So the first time you call your function, if you ran it, let's see if you can run this, and you'll see when we ran this number. Parallel loop. Oh, key mappings are a little off, I think. Notice how 0 took a lot longer than the rest. It's compiling now, and then it's running those compiled versions. So you see the just-in-time in action. It's the first time is the first. But that's a couple of seconds there. We've lost those. So there's nothing we can do. We have to compile, right? So that's a constant, more or less constant cost. So if you had a bigger grid, it'd be better. Right. Questions? Who's going to try number? Nobody? Yeah. Give it a shot. Even if you have a script that was doing something post-processing, but it's kind of slowish, give it a shot. If you're reading files and it's just basically reading files, you're not getting a speed up, obviously. If it's pure post-processing, you might not see anything. But if it's there, something complicated to be done. Yeah. Okay. Well, that was kind of OpenMP, if you want. So let's do really MPI. Really MPI, there's no ifs or buts. Well, no, there's ands and in addition for MPI. MPI for Pi it's a fantastic package. MPI, who here took the MPI track? If you haven't taken MPI is the way that you can parallelize across nodes. So everything so far needed a separate node, needed one node. The cores have to see the same memory. That's how they communicate. That's how it works. But if you have to scale up your program to use even more cores than are on a single node, or if your application simply doesn't fit in the memory of one node, you have to distribute your data. MPI is the way in which you program that. It's a library that makes its use in C and Fortran a bit annoying because you have to pass a lot of parameters to the function calls, like what's the type of the thing you're sending, how many you're sending it, where's the pointer to the data, it's all pointers. But because it's a library, everything is a function call, it wasn't that hard to wrap those function calls into a Python package. All that Python package has to do is to say, okay, you want this to happen in Python, I'm calling the MPI library function for that. So not a hard transition to make, and that's what MPI for Pi did, and more. So it's a wrapper around the C or Fortran library API that MPI gives, message passing interface gives. So it can do things like sending a message between, oh, by the way, a message is what you call data. So if you want data from process 0 to go to process 1, process 0 has to send that data. It's called sending a message, and process 1 has to receive that message. So that's why it's called a message. Messages are what transports the data. So there's point-to-point messages you can send, so from one process to another. So one of the things that is going to be different in this, if you haven't taken the MPI track, I should point this out. When you're running in parallel with MPI, something funny happens. So far, we had a single Python script, and then at some point, stuff happened in parallel because we used multiple cores. MPI sort of puts that on its head. It says, it's not the code, it's the workers. We've got processes. They are started. They can be on different nodes, and they are giving a program. So each of them gets the same program to run. So from the very start, there's workers, processes that are running a code, and they have to communicate. It's not a single starting code that then spawns workers. although that is a way that is possible now. But anyways, that's not how you typically work. You get your workers first, and they start executing things. So between those workers, you can send messages. You can send messages to all of the workers at the same time. That is called collectives. And what is kind of nice in the way it's set up is that because MPI is a library, if you know the library function in C or Fortran, it's kind of pretty much the same name in the MPI for Pi. It's just a little bit more object-oriented. So this is how it works. One of the things you have to do when you have your workers started is they have to know that they all exist and where everybody. They have to have a way to communicate. At first, they don't know which processes are part of their group of processes, and so there's this concept of a communicator that makes this possible. The communicator allows processes to communicate with one another, and that has to be set up by a call called MPI init. So in the MPI versions, you always have an MPI init that is called by each of the workers, and that calls the library, and the library tells everybody who they are and how they're sort of connected to everyone. It takes care of that. In MPI for Pi, that MPI init is done automatically if you import capital M, capital P, capital I. So MPI, you import that. It also does the initialization. If you just do import MPI for Pi, you don't get that. So it's a bit funny. So everybody imports capital MPI from MPI for Pi. And then you need that communicator, and the communicator that is set up in MPI for Pi is mpi.comworld. So MPI is an object. It's an object-oriented form of MPI. And comworld lives inside that object and is the communicator. Now, I find this a lot to type, so I usually abbreviate it or assign it to a variable com. And I don't know how deep everybody's familiarity is with how Python works with variables, but variables are just giving names. So I'm not copying anything here. Com is just another name for the same thing. It's just a shorthand. That's what Python's variables are. They're just names. Okay, so every process runs the same code. So we'll have a Python code. They all run the same code. They will have this at the beginning of their code so that they can figure out who they are. But right now, they all have a handle on this communicator, but they still don't know what they're supposed to do. So the only thing they could do at this point is do exactly the same thing, which is pointless. Just one worker could do everything. So the distinguishing thing for each process is called a rank. So you can think of this as these processes are living on a line. The first one is process 0, rank 1, rank 2, etc. until size -1. It starts at 0 because it's 0 based in Python as well as in C. How do I figure out my rank? Well, I'm asking the communicator, where am I? What's my rank with getRank? So that gives you the rank. Now that each process now has a different number in that rank, and so that they have to use that single number to figure out what they're supposed to do. They are on their own. There's the communicator. He will tell them who they are, like what their rank is, and based on that, they have to figure out what to do. This makes the MPI programming a little bit more elaborate because it has to do that figuring out itself. Once it's figured that out, it might figure out that it needs to send some data from itself to one of the other workers, and so that's the send command. So you can send any variable using the communicator. That's the main thing, sending a variable, and you have to say where it goes, so the destination is another rank. So if you want to send from 0 to 1, to rank would be 1. And how would you specify that it's 0? That's because this call is done by process 0. Okay? So there's no from here, because it's called by one of the workers. They know their rank 0. When they are sending, they're sending from themselves. So there's no source in here. But if you've seen the MPI stuff, this is very different from an MPI send in C or Fortran. In C or Fortran, you have to say, okay, here's the pointer to the variable. This is the type of the variable. This is how many of this variable I want. This is maybe there's a status that you need. In Python, because it's dynamic, the send function, the Python send function that is going to call MPI send, can figure out and look at this variable and go, oh, you're a double. I'm going to send a double. Oh, you're a string. I'm going to send a string. How long are you? Well, I can figure that out. Python has introspection of its variables, and so you can see what it's supposed to send and do all of this drudgery of figuring out what the types are for you. It can send anything, as long as it's not like a socket or something. It can send lists, it can send NumPy arrays. There is a downside. It sends them by packing them up in some sort of way and then unpacking them on the other side. So there's a little bit overhead. But remember, we're starting from Python here. We already have lots of overhead. So that's not always the worst case. How do we receive it? So with MPI, this is kind of funny, especially if you see it for the first time. Process 0 could be sending a message. If process 1 isn't waiting for it, it'll be locked. Oh, it'll be stuck there. It'll be deadlocked. So it has to be actively received. There's no inbox or something like that. It has to actively be waiting for that message. How does that work? Well, you just say, okay, I want to receive something from a source, just has to know where it has to come from, and then put that in a variable. Here's where the unpacking happens. So the sender sends it in some sort of a format. We don't see it, but you could read the Python code if you want. It sends it off, it packs it up. That packing has in it all of the information of the type that gets unpacked here, and the variable has the same type as the variable that's sent on the other side. So again, all of this dealing with messages, setting up special MPI types, none of that is needed here. At a cost, it all happens behind the scenes and there's wrapping, but at least when you're doing things like prototyping, this can be very helpful. The send and receive must match, that's no difference. Or the function will hang. One thing you can do is, if at a certain point in your code, a message has to be sent and received. So suppose you have an application where everybody has to send a piece of data to the right. That means also they have to receive something from the left. There's a send and receive. It's one operation. So there's a send receive. They can do essentially the same thing. And another thing that is very useful and common is that you might want to have your distributed data, say every process has a number, and you want to add them all up. And that's called a reduction. You have a bunch of data, you want to reduce them to one point. And so there's an MPI reduce, but in the MPI for pi, that's just a reduce function inside of the communicator. So you give it what values you want to sum, what you want to do with it. You can sum, you can take the product, you think you can take or, and, things like that. Has to be able to commute. And then where do you want the result to live? So you can imagine that you want to sum up all the variables and only have one process know what the answer is because it's going to print it out. But there might also be cases where all of the processes have to know what the sum is, or maybe the maximum of something is, because they have to use it in some sort of decision-making, like an iteration. If you don't have to do that, if one process is enough, or it has to know what the answer is, that's what you specify with root equals 0. So they all go to rank 0. There's a reduce all, so an all reduce that would send it to everybody. Okay. So that's MPI for pi. If you know MPI, you're going, hey, that's kind of nice. That's pretty simple. If you don't know MPI, this might be a nice way to sort of get started with it. But these processes do not have to live on the same node. This is the advantage of doing this sort of explicit MPI communication. You're not limited to a single process anymore. Obviously, this sending of data is going to cost some time. There's another part of the code will do actual computation on the data that lives inside each process. Okay, so we've skipped having to figure out what the binary layout of the data is for MPI for pi. So that's nice because Python can do this introspection thing, and we don't have to. We have to not worry about the types of things in the default way. So here's that same example. Again, sorry that fell off the slides a little bit. We're doing exactly what I said. We're going to send a message to the right. And what are we going to send? We're actually just sending our own rank, which now that I look at the code is a bit confusing. So each process is started. So however many processes I start, they all will do the same thing. They will initialize their communicator with this import line, and I'm just putting that into COM, but I could also just use MPI COM world everywhere. They get their rank within the set of processes. They can get the full size, how many of them are there, and then they will figure out, okay, who is on the left of me? Well, sorry, who's on the right of me? Well, that's my rank plus 1, but that might not exist for the last one, so that's where this modulus stuff comes in. It basically means that what's on the right of size minus 1 is 0. Okay, that's what that does. Similarly, on the left is minus 1, but I don't want negative numbers, so I add size and I take the modulus, and that does the ring in the opposite direction. Then I'm sending and receiving, so rank is being sent here. This is why it's a little confusing maybe, but that's the data that's sent. Where is it sent? It's sent to the left, but I also need to get something. Where am I getting it from? I'm getting it from the right. So the rank R is the rank of my right neighbor, and then it's going to print what its rank is and what the rank is of its neighbor, which we can't see here. Now, what I skimmed over is how do we start our workers? I said the workers are there. They are there from the start. Where do they come from? They come from MPI run. So it's a utility that comes with any MPI implementation. Sometimes it's called MPI exec. Sometimes it's wrapped around in a function called srun, which hooks into the scheduler. But MPI run is fairly ubiquitous. And you tell MPI run how many workers there should be. NP1 here, in this example, says just one worker. One worker in this sort of loop-around architecture is its own neighbor. So when I'm running my MPI pi rank pi, it knows it's rank 0, and it's received its own stuff. The send receive could have blocked here if it was a separate send and receive, because I mentioned you're sending a message, you're waiting for it to be received, but you're the receiver, but you're sending. So you never get to the receive. It would like the send receives, figures out, oh, you're sending to yourself, idiot. Something like that, and goes, you already know what it is here, I'll just copy it over. But it works, so it gets rid of the deadlock. If I have 4 processes, it gets a little bit more interesting. So MPI run NP4, that's what it should say, launches 4 processes. Those are workers. They each execute this line of code, so Python, that each of these Pythons are executing the same code. So the Python in the middle here, just to reiterate, is essential. Because each of the processes has its own Python running, they each have their own interpreter. They're not locking each other's interpreter. They're separate processes. This is why this can work. This is why it's different from threads. They're their own process. Each is interpreting separately and at the same time. There is no locking in between the two. That is why this works. Anyway, and then they send the right things over to the left and the right, and that's how that works. In a longer version of this workshop, we would try and do MPI for pi, but we've not all done MPI, so that didn't really make much sense. And if you've done it, you'd have an idea of how to split things up, and it's a little elaborate. So in principle, this works just fine. If you want, if you have time beyond working on the challenge, which you shouldn't, do the challenge if you're doing anything. You could try this and it will work, but it would work very similar to the C and C++ or Fortran way you would do this. And now, so MPI for pi, people use it, but they use it when they already know that they have a Python script that does what it needs to do, and they're happy with the performance. If you're starting from scratch and it's something that is really performance sensitive, you probably are going to do it in C++ or Fortran. But what's really almost deceptive about MPI for pi is that if your MPI, one of the things that is expensive in MPI is the communication. It takes some time to send the data. So when you're trying to figure out your scaling of your code, you increase the number of processes and you see how it scales. The communication will be your bottleneck and will limit how you can scale. But because the Python part is slower, you'll actually get better scaling typically from MPI for Pi applications than from MPI applications. So it's still slower than C and Fortran. We can accept that sometimes. It's the reality for Python code. But there's hope when you don't have such a tightly coupled application like the diffusion equation. So if you have a reasonably efficient serial code, if you're happy with it, if it's calling other code to run, if it's calling a library that is the bulk of the code, when that's all done, but now it has to be running in parallel, that's fine. And if it's sort of independent, you can use different packages within Python. If it becomes an application and it's embarrassingly or pleasingly parallel, depending on how you want to call it, there's applications like GNU Parallel that are worth looking at. And you're just going for throughput, right? You already have a efficient enough unit of work, and now you need to do a whole bunch of them. When you're doing big data analysis, you might want to use a framework in Python like PySpark that can help you, or you actually find that most of the time you're just dealing with files and you're reading them in, and that takes the bulk of the time, then that's not going to get slower or faster because you're in Python. If you use all of the tricks that John Case was talking about, don't open and close a file for every byte you're reading. But if you do it well, then you're not hitting the bottleneck of Python. You're just hitting the I/O bottleneck. And if you're using optimized packages that just have a Python interface, so they are calling compiled code, or they're compiling it just in time or behind the scenes. A lot of the machine learning and neural net packages are of that type, where you specify how the computation should happen, and then somehow miraculously within the framework it gets compiled, put on a GPU, and runs fast. If that's the case, the fact that you're in Python is only a bonus, and you actually want that front-end flexibility to be able to have the back-end do things that it should. Okay, so we're going to look at a few last things. This is more of a, hey, you can also do this within Python. So these are going to be a few ways to implement this idea of having well-defined tasks that are not too small, and you have a bunch of them. So the multiprocessing package is one of those, and we'll look at them quickly. We'll skip a few slides of the details, but so multiprocessing is kind of an early answer on, hey, threads don't work in Python. Why do threads not work in Python? Because you have the global interpreter lock. So why don't we start a new Python interpreter? Well, a Python interpreter is a process, very similar to the MPI thing I was just saying. So we pretend they're threads, but secretly they are processes that are running, and we, by some magic, make it work. That's multiprocessing. So they're pretending to be threads, but they're processes behind the scenes. Because they're processes, they have their own memory, and they run concurrently, and each have their own lock. How do you get a thread in this case? You don't. It's a process. How do you get a process in this package? There's a function called process. And it's very similar to thread. So if you've looked at threading, this is going to be similar. If you've not, you'll see that it's a bit, at first, a bit elaborate. You need, where's my example? Here's an example. I have a function f. F computes the square of x, and I want to do that for 50 numbers. I want to do them in parallel. Each number can be done in parallel. What I have to do, and this is how threads work, if you do them at a low level, you have to create a process. You have to say what function that process has to do and what arguments. That's a process not running yet. It's just ready to do stuff. I'm going to put it into a list so I can communicate with those processes, and then I'll start them. When they start, it launches this new process. It's now running independently. It's not waiting for that process to start. So this loop basically creates and launches 50 processes that are running at the same time. Now, if you don't have 50 cores, the operating system will do something so that there's interleaving, but it looks as if 50 things are running at the same time. None of the locking is happening. How do I know they're done? Well, I have to ask for each of these processes to rejoin, I don't know what to call it, let's say the master process. So for every process, I have to have it rejoin, and then I know they're all done. If I don't wait for that, and I kill this process, I'm at the end of the script, Python stops, it kills all of its children, they call it that, I didn't come up with that, which means none of these things are actually done. So this is your wait command, essentially. Now, it's not very nice. There's 50 things we have to do. We would write a loop for it. We'd want to parallelize it. There must be a nicer way, and there is. This is not how you use it. This is what happens on the low level. And if you had threads that do very different things, like there's a GUI thread, and there's a printer thread, and there's a computation thread, like in a GUI setting, you would do this, but you only have like 3 threads to launch. It's fine. But if you don't want to do this for every chunk of your data. So instead, you want to use what's called a pool. So a pool is kind of like creating the threads once and then giving parts of work to them. So it works very similarly at first. We have our function again. We're importing pool. I'm also importing CPU count so I can figure out how many cores I have. I create a pool, which I will call P, of that many threads. They're now ready to do stuff, and I can use a map function. So the map function will take a list, or a range in this case, and apply a function to each of them. But it will do it in parallel because I'm asking the pool to take care of that. So if you have a function that has to be applied to every variable in a list, this will do it in parallel. It's a bit of a different way to think about parallelism. It's not quite the same, but if this is a substantial body of work you have to do, and it's just a list of data or list of files you have to go through, it can be a nice way to get things done without having to leave Python. I'm going to skip the shared memory part. Just want to say that in threads, threads are meant to be sharing memory, that they're on the same node, they're sharing memory, that's how they can communicate. But once you have separate processes, their memory is separate, so they cannot communicate through a variable. Somehow the multiprocessing package has made it possible to do that, and it's a good thing it does. So you can imagine if your processes live on the same node, that node has one main memory. It must be possible to communicate to that main memory. It's just that the operating system has shut that off because the processes are supposed to run in silos, and that's good for security and all of that. But it must be possible, and it is possible. But every operating system does that a little bit differently. So if you're on Windows or Linux or Mac, slightly different. So this abstracts that out, and it does it by using a special type called a value or an array with capitals. And so you can create an array. You have to say what type it is, but you can access that array. So it's kind of somewhat more explicit. You have to say this is a shared variable, but it still allows you to use shared variables. Now with that come all of the pitfalls of shared memory programming, like race conditions and all of that. So a few of the slides talk about how you can lock things and stuff like that, but I wanna not go over that. Questions? Got 2 more packages for you to look at. So multiprocessing really good if you have like substantial work to be done in Python, and this is kind of the type. Numba is good if you have like one big function with like loops and if statements. Excuse me. One thing that they all did so far is they were very imperative. Like we told it exactly what things have to be done in what order, and some could be done in parallel. We're very specific. Another way to look at parallelism is so-called task parallelism, task-based approaches, and they're more common than you would think, even if it's not called task-based. Like Yeah, so imagine that we have stuff to do. Let's call them a task. Okay, we had stuff to do for the diffusion equation, that's computing the stencils, but they're kind of lightweight, so bundling them up would be a bit overkill. But imagine that we had tasks, a whole bunch of tasks that we have to do that have substantial weight. Now, if they're all independent, multiprocessing is probably the way to go. But imagine that there's no dependencies on these tasks. So some tasks have to be done, will produce an output that then other tasks need. So just put them into a big list and then run them in any order will not work. But some of them can be done in parallel. How do we know which one can be done in parallel? We have to step away a little bit from this idea of imperatively programming this and saying this has to happen and then this has to happen and that has to happen, because that would be really tricky to do if there's dependencies, really tricky to get right. We'd want to automate that. So that's really what the task-based approaches are about. You want to specify what needs to be done, but not do it. Say this has to be done, and then somehow encode the dependencies between the tasks, and then have some package take care of it. It says, well, from that, I will have a task graph with dependencies, and some parts of the graph can be done in parallel, and others cannot, and I will figure that out and do the best I can. That's what you want. But for that to happen, you'd have to specify the tasks, not do them yet, just say what has to happen, and then at some point say, okay, run. Scheduler or whatever it is, figure out how to do this with as much parallelism as possible. That's what these task-based approaches do. So we have to declare somehow the dependency graph, and then we have to execute it. And I think packages like SnakeMake do that too, but I didn't include it here. I'm looking at 2 other packages. Now, if you have an environment that already has dependencies in it, and I'll give an example in a second. So the dependencies are obvious because before you can compute variable y, you just need variable x. Then the algorithm itself sort of has in it the dependencies, but as soon as you hit the first line, you start computing it. So any chance of parallelism is gone because it does things line by line. So that's a case where these packages can be useful. So Dask is the first one I'm looking at, the Dask package. Here's a package, Dask. It has a bunch of data-specific interfaces, API calls. It can deal with data frames and stuff like that. That's the high-level stuff that you want to use. I'm just going to show you what it does behind the scenes to make the parallelism work. So on that level, it has a thing called dask.delay. So here's my algorithm. I'm going to add 2 numbers, x and y. First, I'm adding 1 and 2. I'm storing it in a variable x. Then I'm adding 2 and 3, and I'm storing it in a variable y. And then z is adding x and y, and then I print out what z is. But if you think about it, we could compute x and y at the same time, right? They're independent. They both have to be done before z gets done, but they could be computed at the same time. But the way I've written it here, x gets computed, and y isn't even in the picture yet, and then y gets computed. That's why this imperative stuff doesn't work. When you're using Dask, let me move this. I'm trying to move this. How do I move this? In Dask, you have the same algorithm. Doesn't change, but you prepend them with dask.delay. So you have your add function, but you say, no, I want a delayed version of this add function, and that's going to be my x. Now, x is not going to be a number. It's a delayed object, but it looks the same. Y is similarly a delayed object. Z is a delayed object. So what this does is it just specifies what you want to do, but not do it. How do I get it to do it? I say z.compute. So that goes, okay, z compute. I was delaying x and y computations and adding them. X and y were computations themselves, but hey, in the graph I can see that there's no dependencies between them, so I'm going to do them at the same time. That's where the parallelism comes in. Now, obviously, this is a small example. You're not going to get any speed up here. You're not going to see it, but it does do it. And if you had a much more heavy task or a more complicated task graph, the compute takes care of figuring out all of the parallelism. That makes sense? So you specify your tasks, and I like this about the task package, and Ray does it also. The algorithm hasn't changed, right? It's just the delaying that we're putting in there so that there's something that can figure out what can be done in parallel. Yes, so it does it. It has a whole bunch of other features, and those are the features you already want to use. When you're working with data frames, if you've got something in pandas and it needs to be parallel, look at Dask. If you've got, so there's a bunch of stuff it can do. It can be dynamic. It works well with NumPy, SciPy, scikit-learn. Lots of it in it, but as I said, these packages have good documentation and tutorials that you can find. If this is the way you're going, you'll be able to do it. But this is how it gets its parallelism done. And the same is true for the last thing I will mention, which is the Ray package. It aims to be a little bit more general. It can also have some sort of state. So with Dask, it's pure functions in a sense, sort of. Ray is a little bit different, but in its heart, it's the same thing. It's easier to put up a distributed version of. Oh, this says 10. Yeah. Okay. So it's the same, the same mechanism. It's just a different syntax on this level. At a high level, its features are a little bit different, but that's the same. So that was a walkthrough from performance, figuring out where your performance deadlines are, trying to fix them in different ways, and depending on the package you use, you have to do it differently, all the way up to task-based parallelism, where at a high level, you're really just going to work with data frames, but it can do things in parallel because of the delayed nature of the packages. Thank you.